Right, welcome back. In the last lecture, we ended with these limit and continuity laws, right? And we didn't prove them back then. So the assumption is this limit and this limit exist, okay, exist, this equals b, this equals c, and a variety of other limits are expected to exist. All right, so for example, so the first such limit is the sum of these two is b plus c. Yeah. So how does one prove such a fact? Well, the rough idea is f of x is approximately equal to b when x is close to a. This is approximately equal to c, so the sum is approximately b plus c, but we need to keep track of the errors in these approximations, so to say. So choose delta small enough so that whenever x is delta close to a, f of x is very close to b. How close? Epsilon by 2 close. And likewise g of x is epsilon by 2 close to c. Why can this be done? You can certainly choose a delta so that the first thing holds. This is by definition of the limit existing. You can choose another delta so that the second one holds, and then you can choose delta to be the smaller of these two deltas so that simultaneously these two things hold. Now the rest of the proof is rather easy. For all such x, let me put a norm here. This is less than by the triangle inequality. So this is less than epsilon by 2 plus epsilon by 2, which is epsilon. Yeah. So this is how you prove the first law. And if you recall one variable real analysis, this is exactly how you prove it in that context as well. The proofs more or less look the same. There's not much of a difference. So what's the second one? The limit as x approaches a, lambda f of x is lambda b. Again, the proof is rather easy in this case. Without loss of generality, lambda is not 0. Why is it not 0? Because if it is 0, the left hand side and the right hand side are trivially equal to each other. Yeah. Right. So if lambda is not 0, then surely there exists a delta almost by definition, so that when x is delta close to a, f of x is very close to b. How close do we want it to be? Less than epsilon divided by lambda. So by multiplying by lambda on both sides, we get what we want. Okay, so it's very straightforward. What about this one? The dot product. This is also similar to your one variable calculus proof, except for a small little point. So once again, the way you prove these limits is the intuition is f of x is approximately b, g of x is approximately c, so the product is approximately b times c, but you need to be able to keep track of the errors made. So let's define two error vectors. How far f of x is from being b and how far this is from being c. Note that whenever x is very close to a, h1 and h2 are very small. Yeah. Anyway, so let's What do we want to do? We want to take the dot product of these two, subtract b dot c from it, and you want to make it as small as you want, right? So simply write it as b plus the error dot c plus the error. This is b dot c's cancel out. Now by the triangle inequality, so all these steps are more or less the same as what you would do in one variable calculus. The only little thing in multivariable calculus is in this step, the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality would say that this is less than the product of the norms right. Now what do we want? We want the sum of these three to be less than epsilon. Individually, we can arrange this to be less than epsilon divided by 3, this to be less than epsilon divided by 3, and this to be less than epsilon divided by 3 whenever x is very close to a. How can we do this, right? Surely, by definition of this limit being equal to this as x goes to a, when x is very close to a, in other words, there is a delta so that when x is delta close to a, this error vector can be made as small as we want. In particular, we can make it smaller than epsilon divided by 3 times norm of c. Again, we assume without loss of generality that norm of c is non-zero. If it is 0, this will become 0 anyway, right? So if it's non-zero, you can simply choose a delta to be so small so that this error is less than epsilon divided by 3 norm of c. Likewise, you can shrink delta. You can make it even smaller if necessary, so that this h2 is less than, this error is less than epsilon divided by 3 norm of b. Again, if norm of b is 0, that's even better, because then this will be 0 anyway. How does one make this less than epsilon by 3? Well, you shrink delta even further if necessary, so that this, for example, is less than 1. It's already less than epsilon divided by 3 norm of c. You can choose your delta to be so small that it is simultaneously less than epsilon divided by 3 norm of c and less than 1, right? Choose the minimum of these two numbers, and then h1 must be less than the minimum of these two numbers, and there's a delta that makes this happen. Then you can make sure that delta is so small that norm of h2 is less than epsilon by 3. So 1, this is less than 1, this is less than epsilon by 3, so the product is less than epsilon by 3. Okay? So that's how you would do it. So it's just directly following your intuition. I mean, there is nothing mysterious going on here. The only tools you have at your disposal are the triangle inequality, of course, the triangle inequality, as well as the Cauchy-Schwarz inequality, and some basic common sense. Right? You can make this as small as you want. That's all. Right. Likewise, you can prove that the limit of norm of x equals norm of b. Why is this so? I'll leave this to you as an exercise. Once again, whenever I give you such an exercise, I urge you to please pause the video and think about how you might do it. Yeah? All right. Lastly, So suppose you have scalar valued functions, they're both defined on the same domain. A is a limit point of this domain. Sorry, this is S. Just write this. This is S. Suppose they're scalar valued functions, and suppose this limit, which is C, is not 0. The last time I told you that the limit of a function depends purely on the behavior of the function in some neighborhood of A. In other words, limit is a local property. It doesn't depend on how the function behaves very far away from this point. Yeah. So as a consequence, because this is the case, for all x which are close to A and lie in the domain of G, namely S, g of x is necessarily non-zero. Yeah, because the limit is non-zero and g of x is very close to the limit as x is close to A, and therefore g of x is non-zero in a neighborhood of A. But one way, I mean, I can prove this, but this implies g of x is non-zero for all rather x b. Okay, so the point is so there is some open ball which intersected with S. For all such x, g of x is non-zero. Why is this so? I told you orally the rough idea of the proof. Again, it's a good idea for you to write it rigorously. Okay, right. Now that that is the case, we can make sense of f divided by g, and this question makes sense in the first place. Otherwise, this doesn't even make sense. Yeah. So how does one prove this? Again, right. So without loss of generality, f is actually just 1. Why is this so? The same as b. Okay. Why is this without loss of generality? The idea is if f is not the function 1, that is, if we manage to prove that this is the case, and we already know, sorry, there's no vector, this to be the case, then by using one of our previous rules, if you multiply f with 1 divided by g, then you get b divided by c. So, okay. So it follows from one of our previous rules, if you wish, the product law for limits. Okay, so in other words, our question has been reduced to simply looking at this. Yeah. Right. So once again, all we have to do is to so suppose we take 1 divided by g minus 1 divided by c. Right. So we want this to be less than epsilon, right? So somehow we need to handle this term, right? So first of all, there exists a delta, let's call it delta 1 if we want, such that g is very close to c. How close do we want it to be to c? So g of x minus c is less than, let's say, c divided by 2, mod c divided by 2. Yeah. So this means if you take mod of g, this is the so-called reverse triangle inequality, if you will. you can, there are a number of ways to do it. Maybe I'll do it this way. Actually, maybe you can do this as an exercise. Why is this true, right? From this, why is this true? It's actually very easy, right? G is basically mod C divided by 2 far away from C. So at most it will reduce to mod C by 2 and increase to 3C by 2. Again, please do this as an exercise. Yeah, it's rather straightforward. As a consequence, this is less than C minus G divided by mod C square times 2 whenever this happens. Okay? Right. Now, this is surely less than epsilon whenever for some delta, right? Maybe that delta needs to be less than delta 1, no problem, but this is true. Why? Because we know mod G minus C can be made as small as we want, in particular less than epsilon times mod C square divided by 2 for some delta, right? So again, this is not very difficult. You just have to get used to these sorts of things. Okay, right. And we can also, well, here is another exercise if you wish. It's the same kind of proof. If lambda from S in Rn to R is continuous, and F is so, then so is lambda of x times F. Okay. So the previous limit laws that that we wrote and proved, they can prove similar laws. There are similar statements for continuity, and these limit laws can be directly used to deduce the laws for continuity. Yeah. So in addition, we also have this sort of a thing. Namely, if you take the product of two continuous functions, it's continuous. Yeah. Okay. So what good are these limit laws? Now we have several examples of continuous functions. Recall that continuity in more than one variable is a dicey affair. Heck, even the existence of limits is a very dicey affair, right? Because we saw something very reasonable looking like xy divided by x square plus y square, and the limit as x comma y goes to 0 comma 0 did not exist. Despite individually, if you fix y and you take the limit in x, or if you fix x and take the limit in y, these limits existed, and yet the multivariable limit did not exist, leave alone continuity, right? So we need some laws that help us deduce when things are continuous. Right. So for example, this is not quite an example, this is something we've already proven, but it could have been deduced in another way. Remember, this f dot g converges to b dot c. This could have been proven by noting that it is f1 g1 plus f2 g2 plus so on until fn gn. This is b1 c1 plus b2 c2 plus so on until bn cn. Given this fact, right, this is, rather, this is for limits and likewise for limits. Okay. Given these facts, notice that f1 times g1 will converge to b1 times c1, f2 times g2 will converge to b2 times c2, and so on from this fact alone. And we know that the sum of two limits equals the limit of sums. This is a sum of n limits. So induction on n plus, let's say this is star plus star plus the sum rule, sum law, will allow us to prove this. Okay. So while we proved this separately, we could have done it by an application of these laws. Okay. So how do you why do we need to induct on n? Because we proved the sum law for a sum of two functions, but you have n functions here. Okay. So this also requires a small proof. Again, I'm leaving this as a very little exercise. Yeah. Okay. The identity function, namely f of x equals x, is continuous on all of Rn. Why is that so? Because each component is a one variable function which is continuous, and we know if a one variable function is continuous and you pretend that it's a function of more than one variable, it continues to be continuous. This is something we proved. And a function is continuous if and only if each of its components is so. Yeah? Linear maps are continuous. Indeed. Suppose we consider this by linearity. Right. So why is this equal to 0, right? There are a number of ways to do it. So for example, choose a basis, right? So h vector is h1 times e1 plus h2 times e2 plus h3 times e3, so on. So by linearity, you get this. And happily enough, this goes to 0. Why? This is a one variable function. Likewise, this goes to 0 and so on. So by the sum laws of limits, this is 0. And therefore, linear maps are continuous. Right. Okay. So this is perhaps the fourth example. Polynomials are continuous. What is a polynomial? What is a polynomial? A polynomial in more than one variable, rather than defining it in its full generality, which will involve some bookkeeping. So for example, if I take two variables, what is a polynomial? Okay. Now this is for example, this is an example of a degree 3 polynomial in x and y. More generally, a polynomial is a sum of this type, x raised to I, y raised to j, and one way you can say that it's a finite sum. Suppose, let's say I comma j is both of them are less than n. This is a polynomial in two variables. It's more convenient sometimes to rewrite, instead of summing it like this, x raised to I, y raised to the degree, let's say instead of aij, I can write it as aid, d minus I, sum over the d's and then sum over the i's, for example, sum over the d's and then sum over the i's, and sum over d's, finite sum. This is one more way to write a polynomial. Nonetheless, now we know what a polynomial is. It's simply you take any power of x, any power of y, multiply them by some numbers and add them up, and it must be a finite sum. That's what a polynomial is. The degree of a polynomial is obtained by taking this number plus this number and taking the largest possible number you can get. For example, here it is 3. I mean, of course, actually we don't even need this because I've already put this. For instance, it's 2 plus 1, which is 3. 3 is the largest such number you can get, right? This is for two variables, but the same definition holds for any number of variables. All you do is you take some arbitrary power of the first coordinate, multiplied by some arbitrary power of the second coordinate, then the third coordinate, etc. Then multiply all of these by some real number and add up, and it must be a finite sum, right? Why are polynomials continuous on all of Rn? Why is this so, right? This is by induction on various things. Okay, how exactly is it by induction? First of all, these things, suppose I take some number, this is a real number, x1 raised to some power, x2 raised to some power, xn raised to some power, maybe xm raised to some power. These are called monomials, and these are continuous. This fact itself requires induction. Why? Individually, these are continuous functions. Why? Because they are one variable continuous functions, and we know polynomials in one variable are surely continuous. This is a well-known fact, right? Now, by induction, you can prove that the product of n continuous functions is continuous. We've already proven that the product of two continuous functions is continuous. We just have to extend it by induction to n. And of course, scaling a continuous function by a real number is continuous. So monomials are continuous functions. And if you add finitely many monomials, you get a polynomial. And therefore, by induction, the sum of an arbitrary but finite number of continuous functions is continuous. And therefore, a polynomial is continuous. Yeah. Now, these properties imply that rational functions are continuous away from the zeros of their denominators. What do we mean? If I take a ratio of two polynomials, let's say, take your favorite polynomials, and let's say pi plus x minus y or something. this is a continuous function provided this is not 0. In other words, wherever this is not 0, right, on the subset of Rn where this is not 0, this is a continuous function. Now, this is a slightly dicey affair. Okay, why? When we say something is continuous at a point, right, either that point is an isolated point of the domain, or if it is not an isolated point of the domain, it's a limit point of the domain, and we have to check the definition of the continuity. Okay, what sort of points are these where the denominator is non-zero? Namely, if a polynomial is not 0, what is the set of points in Rn where a polynomial is not 0? I claim that set is actually an open set. In other words, if you are non-zero at a point, you will continue to be non-zero in a neighborhood of that point. Why is that so? That's because polynomials are continuous. Since they are continuous, if they are non-zero at a point, that is, what does it mean to be non-zero? Their norm is non-zero at that point. Since the norm is continuous, if you take a small neighborhood around that point, the norm will continue to be non-zero. Okay, we have already proven something similar to that in one of our previous proofs. So that's the reason. So in other words, the places where a polynomial is not zero is an open set. So they're all so it makes sense to talk about continuity. These are not isolated points, if you will. Okay. All right. So we'll stop here. Thank you for joining. We'll continue the next time.